Welcome back to Virtual Lab. In today's video, we will be performing a stereoselective reduction of camphor. The purpose of today's lab is to reduce camphor to a mixture of isomers, isoborneol and borneol, and to determine which is the stereoselective product by melting point and NMR. Camphor contains a carbonyl that can be reduced to an alcohol by nucleophilic attack by a hydride ion followed by hydrolysis. The hydride ion can approach the carbonyl carbon from the top or the exo approach, which is sterically hindered by the methyl group on the bridge, or from the bottom or the endo approach, which is not sterically hindered. We can expect our major product to be formed by the endo process because it is not sterically hindered. This major product would be isoborneol. However, we will still get some of the exo-attacked product, which would be borneol. We can confirm which product was stereoselectively produced by melting point and hydrogen NMR. Borneol's melting point starts at 206 degrees Celsius, and isoborneol's melting point starts at 212 degrees Celsius. If the product starts to melt at 206 degrees Celsius, the product may contain mostly borneol. If the product starts to melt at 212 degrees Celsius, the product contains mostly isoborneol. The hydride that is added to the carbonyl carbon will have different electronic and chemical environments depending on whether it adds endo or exo. We can see this in the hydrogen NMR. The exohydrogen on borneol will have a chemical shift at 4 ppm on the HNMR. The endohydrogen on isoborneol will have a chemical shift at 3.6 ppm on the HNMR. We will see peaks at both shifts, but one peak will be much larger than the other. The larger peak is the major product. Please refer to the lab lecture for how to calculate the percent composition of the product from the NMR peaks. The reduction will also be confirmed by IR spectroscopy. The materials listed here are what we will be using in today's lab. The equipment for today will be the balance, Erlenmeyer flasks, spatulas, weigh boats, graduated cylinders, ice bath, hot plate, vacuum setup with Hirsch funnel, pasteur pipettes, and a beaker. The chemicals for today will be camphor, methanol, sodium borohydride, water, diethyl ether, sodium sulfate, which is anhydrous, and our products borneol and isoborneol. For analysis, we will be using the Nicolette IR spectrometer, the MELTEMP, and a benchtop NMR. As always, there are specific safety concerns for today's lab. The hazards associated with the chemicals are: camphor is flammable, combustible, has acute toxicity, and is an irritant. Methanol is flammable, has acute toxicity, and is an irritant. Sodium borohydride has acute toxicity, is an irritant, and is corrosive. Diethyl ether has acute toxicity, is flammable, and an irritant. Borneol is flammable and an irritant. Isoborneol is flammable and an irritant. We will be using the following protective measures to ensure our safety. We will be wearing proper lab attire, gloves, and goggles. We will be working with the chemicals in the fume hood. Before we jump into today's lab, let's go over some general lab safety. Here comes a student that is almost ready for lab. She is wearing pants without holes in them and shoes that are closed toe. However, her hair is not tied back and she is wearing a long-sleeved sweatshirt that is not flame retardant or graded for lab chemicals. On her second try, the student is now ready for lab. She ties up her hair with hair ties so that it is out of her face. She puts on her lab safety goggles and she puts on her lab coat, which is fire retardant and is graded for lab chemicals. The student also double checks her list of chemicals for today's lab and puts on her lab gloves. Let's review some proper lab attire. You must be wearing shoes with closed toe and no height. This means no heels, no platforms, no Crocs, no peep toes, and no sandals. You must be wearing pants or floor-length skirts that do not have any holes. Short sleeves are preferred. If you have long hair, it must be tied back. If you have a long beard, it must be tied up. In every lab, you are required to use the proper PPE, or personal protective equipment, gloves, and goggles. Now let's go over the lab safety stations. The emergency eye wash and safety showers can be found in one of the front corners of your lab. If you get a chemical in your eye, go immediately to the eye wash station, pull down the eye wash station door. The water will start running immediately. Keep your eyes in the stream of the water for 15 minutes. If chemicals are spilled on your body or your clothing, immediately go to the safety shower, remove all of your clothes, pull down the safety shower handle, and throw the curtain around you. In the other front corner of the lab is where you can find the fire extinguisher. The fire extinguisher should only be used if you are confident in its use, the fire is small, or you are using it to escape the fire. Here is where you can also find the glass waste and spill kit. In the event of a spilled chemical or broken glassware, please inform your TA. Your TA will be responsible for cleaning up the mess. First, we will start by preparing our ice bath. This way, our water can cool while we prepare the other reagents and start our reaction. Ice was obtained from the stockroom. Add ice to the container and add water. Adding water will ensure that the entire surface area of anything we place in the ice bath will be cooled. Next, fill the graduated cylinder with 4 milliliters of deionized water. Place the graduated cylinder in the ice bath to cool. Add more ice and water to the ice bath until it covers the level of the water in the cylinder. While the water is cooling, we will weigh out our starting materials. First, clean off the balance with the brush, place the Erlenmeyer flask on the balance, close the doors, and tare the balance. Add about 0.10 grams of camphor to the Erlenmeyer flask. Record the final amount in your lab notebook. Next, we will weigh about 0.060 grams of sodium borohydride into a weigh boat. Place the weigh boat on the balance, close the doors, and tare the balance. We need to be extra careful when weighing the sodium borohydride because of its reactivity and associated hazards. Record the final amount in your lab notebook. We bring our solid materials to the hood so that we can prepare the reaction vial and start our reaction. We measure out 0.5 milliliters of methanol in the graduated cylinder. We use a Pasteur pipette to transfer the solvent to the reaction vial. We swirl the mixture to dissolve the camphor. Once dissolved, we place the reaction vial on the hot plate. Notice that the hot plate is not turned on yet. We very slowly add the sodium borohydride to the flask. We add it slowly to avoid any violent reactions. If you notice the vial rapidly heating or reacting, cool it briefly in the ice bath. Now that all of the reducing agent is added, we turn on the hot plate and set the temperature dial to about 60 degrees Celsius. We allow the reaction to gently boil for 3 minutes. If you notice the solvent level getting too low, add 0.5 milliliters more of the methanol. We did not have to do this in our reaction. After 3 minutes, we turn off the heat plate and allow the reaction vial to cool to room temperature. Once cooled to room temperature, we add the 4 milliliters of deionized water that had been cooling in the ice bath. As we add the cold water, we can see a white precipitate start to form. We need to prepare the vacuum filtration setup so that we can vacuum filter our product. As in previous experiments, we clamp our filter flask to the ring stand, add the neoprene adapter for a tight seal, attach the hose to the vacuum nozzle, place a new filter in the Hirsch funnel, and place the Hirsch funnel in the neoprene adapter. We turn on the vacuum and slowly pour the contents of the Erlenmeyer flask into the Hirsch funnel. Using a spatula, scrape as much of the product into the Hirsch funnel as you can. In order to get the remaining precipitate out of the reaction vial, we cooled an additional amount of deionized water in the ice bath and used it to rinse the vial and pour the contents into the Hirsch funnel. This will also help rinse out any ionic impurities in the product. Scrape the crystals in the Hirsch funnel to test the dryness and to allow the air to flow through the crystals so that the air can dry the crystals. We allow the vacuum to dry the crystals for a few minutes. After a few minutes, the crystals are drier and fluffier, but may still contain water. In order to remove the water, we will redissolve the product in diethyl ether and dry with sodium sulfate. We turn off the vacuum and transfer the product to a clean, dry Erlenmeyer flask. Carefully scrape as much of the crystals from the Hirsch funnel as you can. Measure out 5 milliliters of diethyl ether in the graduated cylinder by transferring with a Pasteur pipette. Add the 5 milliliters of diethyl ether to the product and swirl to dissolve. Add a few scoops of the drying agent, sodium sulfate, to the flask and swirl. If the sodium sulfate is clumping, add more and swirl until you see free-flowing sodium sulfate crystals. Cover the Erlenmeyer flask with a piece of parafilm so the diethyl ether does not evaporate. Before we isolate our product, we need to prepare our product vial. Obtain a new product vial and cap, and obtain the weight using the balance. Record the weight in your notebook. Instead of a product vial, you could also pre-weigh a clean and dry beaker. Using a Pasteur pipette, transfer the ether solution to the weighed product vial. Make sure not to suck up any of the sodium sulfate crystals. In order to get the maximum amount of product, we will add about 1 milliliter more of the diethyl ether to the Erlenmeyer flask to wash the sodium sulfate crystals. 1 pump of the Pasteur pipette is about 1 milliliter. After swirling the ether and sodium sulfate crystals, we will again add the ether solution to the product vial. Instead of waiting for the ether to evaporate from the product vial, we will use air to quicken the process. We turn on the air nozzle and make sure that the air is flowing gently. We hold the air hose a few inches above the product vial because the solvent is almost at the top of the vial. As the solvent level goes down, as it evaporates, we can move the air hose closer to the vial opening. Now that the solvent has evaporated, we can weigh the product vial and cap again. Record the weight in your notebook. Subtract the previous weight of the empty product vial and cap from this weight to get the final weight of your product. Before we move on to analysis, we will clean up our lab space. Empty the liquid waste to the liquid waste container. Rinse the equipment with acetone in the liquid waste. Discard the sodium sulfate into the solid waste. Before we take the background of the IR, make sure that the stage and sidearm are clean and dry. Scroll the sidearm down and take the background of the machine. Once the background is complete, cover the diamond crystal with the product, place a square of paper over the product so that we don't have to clean the sidearm, replace the sidearm, and take the spectrum of the product. After taking the spectrum, clean the IR stage. Now we will take the melting point of our product. Turn on the melt temp. Our product is stuck to the glass product file, so we need to scrape it off with a spatula. Obtain a new capillary tube and tap the open end on the product until you get 2 to 3 millimeters of product at the top. Carefully tap the closed end on the lab bench so that the product falls to the bottom. You can also drop the capillary tube down a glass tube to get the product to fall to the bottom. Once the product is at the bottom, place it in the melt temp and start the temperature ramping on the fastest setting. It will take a few minutes for the temperature to reach the melting point of borneol or isoborneol. When we get to about 20 degrees Celsius below the melting point of borneol and isoborneol, we slow the temperature ramping to 3 degrees Celsius per minute. As we approach the melting point of borneol and isoborneol, we can see the morphology of the crystals start to change, but melting does not occur until we see the presence of liquid. As you can see, the product in the capillary tube is shrinking as the temperature is increasing, but we are not seeing melting occur. Unfortunately, the product is going through the sublimation phase change at a temperature lower than the melting point. We continue to ramp the temperature to see if we will get any melting before the product completely sublimes. We have officially reached the melting point of borneol without observing melting, and our product is almost gone. We have officially surpassed the melting points of borneol and isoborneol and have not observed melting, and have a tiny amount of solid left in the tube. This leftover solid is most likely an impurity. When we take out the melting point tube, we notice that our product has deposited on the cooler upper portion of the tube. Some sources for chemical properties of isoborneol include sublimation in parentheses next to the melting point temperature to indicate that this may happen. In the data section of your lab report, you will need to include the yield and the percent yield. Show your percent yield calculations. Include the IR spectrum of the product, draw the product structure on the spectrum, and label the important peaks. Report the melting point or melting observations. Include the NMR spectra from the lab manual, show the integration of the peaks, and the percent composition calculations. In the discussion section of your lab report, comment on the success of the experiment based on the yield and the percent yield. Make sure to provide a complete error analysis. For the IR, discuss the importance of the IR. Which peaks are you seeing and not seeing? Is it what you expect, and why? For the melting point, discuss what we are expecting to see with the melting point. Discuss what you observed. Compare it to the literature values. For the NMR, based on the given NMR, what percent of the product should be isoborneol and borneol? How does the NMR show this? Thank you for watching the reduction of camphor lab video. Please bring any questions to your TA.